Good afternoon and welcome to this session of Linux Conference 2013. The topic today is teaching robotics and embedded computing with Lego and Arduino, or Lego as you say outside of South Australia. The presenter is Keith Packard, Open Source Technology Centre of Intel Corp. Welcome, Keith.
Thank you, sir. As our fine introductory note said, I'm Keith Packard. I work with Intel at the Open Source Technology Center. I mostly do display stuff, working on the X drivers, X server, that kind of stuff. Today we're taking a little diversion from that. We'll talk more about X tomorrow. If you want to hear about X, that's tomorrow's talk. Today we're talking about Lego and Arduino. A significant diversion for me, not so much in technology, but in role. In this particular program, I'm actually trying to become a teacher. I don't know how many of you have done primary school teaching, but oh my God, it's a lot of work. It really gives you a newfound appreciation for what our teachers go through in taking care of our children until they're the age of 30 or so, below that age. Yeah. Okay, so what is this? This is not my own class. I've constructed a bunch of curriculum for a program that's been going on for a long time. Ever since this hardware, the original hardware is new. You'll see what the original hardware looks like shortly. This is a Lego program for children ages 6 to 12. With a mixture of teaching assistants who range in age from 10 to 18. So you can see there's a little bit of overlap. You might guess that the teaching assistants are former students. And so the teacher of this program is very interested in mentorship and teaching students to become mentors for younger students. The school has a long history of that. And so we as adults work with both the younger students and the older students in learning and teaching, and teaching how to teach and learning how to learn and all sorts of stuff. Obviously it's a mixture of professional and amateur adult teachers. I'm one of the amateurs. There are two professional teachers in this program. It's an after-school program, which means that it occurs after the regular school hours, and the children who are attending the program are not there under duress. They definitely want to be there. It's a very different environment from a day school environment where the children are essentially housed so their parents can go off to work. This is one where the children want to be there. Who am I? I really am just a humble parent. I'm one of the parents. I have two students who are in the school. They are now well beyond the age of this, which I feel gives me the opportunity to come in and teach other people's children without the interaction of teacher and parent going on at the same time. That's very frustrating for me. I've done it a couple of times, and I said never again. I escape any class where my own children are. I run away. I don't want to be a parent and a teacher at the same time. I single task. I do not multitask. I'm a willing volunteer. I've had a lot of time to volunteer at the school. I used to work for HP, and when I worked for HP, that's kind of a part-time job and a full-time teaching job. It was kind of cool. I've since transitioned to a job at Intel where I have a lot less time to actually volunteer in the classroom, and so I've had to focus the roles that I do and things that I find particularly interesting in areas where the school is asking for me to volunteer. I don't have any experience teaching small children. The only experience I have is as a parent, which is completely different from teaching, as I learned out. But what I did do is come into the school with a very open mind. I came in knowing that I was not going to be able to teach any children at all in the first probably 5 years. And so what I did when I came into the school is I said, can I help you copy some papers? Can I help clean glassware in the chemistry class? That kind of stuff. So I started off by doing things the teachers were ending up doing because they didn't have anybody else to do them. So I said, oh, I could do that. I remember I used to publish the weekly newsletter, which we actually printed on paper. And so I would run the Xerox machine and print approximately 400 copies of the weekly newsletter, which some teacher used to do. It's like, really? You had a teacher standing in front of a copy machine for 3.5 hours? No. That's something the unskilled and unpaid laborers can do. And of course, I watched the teachers as they were teaching the children, and tried to do things like they did. Although I didn't have their 47 years of education and 6 years of 47 years of experience and 6 years of education. Fortunately, I'm working in the primary school at this point where the children are between 5 and 12 years of age. The teachers in this age group are all universally nice people. They're used to dealing with children and novices. They're oddly really good at teaching how to teach as well, because they've had a lot of experience in peer teaching. When new teachers come in, they're very used to doing that as well. In fact, I think that's part of their training, is teaching new teachers how to teach, which is kind of cool. One of the things that I started off with a very strong opinion is that discipline is their job, not my job. If I have a discipline problem, that's a professional teacher's problem. They have counselors, they have people with weapons as needed, come in and anesthetize the children and take them away until they're better. So that was a really nice relief, very much relief. If I ever felt like I was, very much like LCA, if I ever felt like I was not capable of handling the situation, there were people there to help me out. I never felt like I was on my own. The LEGO classes, it's a 6-year program, and of course LEGO is totally secondary. The entire purpose of this class is to teach children basic physics and basic engineering techniques, and along the way take these children who are self-selecting to do an after-school class in LEGO, probably a lot like a lot of us as children, teach them a lot of socialization, interaction skills, collaboration skills, teaching skills. As I said, the older students start teaching the younger students. And here's the program that the teacher, Jane Kenny Norberg, has put together. She has 6 years. The first one, they just put some models together. And they're like 5 years old. They're putting Lego models together. So you can imagine going to an after-school class, being given a Lego kit and saying, please put this together. It doesn't sound too challenging for the typical 5-year-old. And in fact, the 5-year-olds typically have no trouble with the models. They have a lot of trouble not throwing the models at the other students. But what they do get is you do get a bunch of education in how the models are put together. So instead of just constructing the models, they're told to construct the models, and then they're asked to explain why the model's put together this way, and how these, how different parts of the model work together, to get some idea of the physics of the actual interconnection of these little plastic pieces. Instead of just building the model and being done with it, they actually have to talk about it and learn about it. The next year they go through some inventive model building where they get to build whatever they want out of the same Lego bricks. That means and they're given a couple of problems, like build a catapult or build a bridge that can support this much weight and that kind of stuff. So they're given a little notion of physics and statics, notions of how you have to overlap the blocks so they don't fall apart and that kind of stuff. The next year they do some motorized building of pre-existing models so that they get an introduction of how motorization changes the problems, how you move from statics to dynamics, and how you have to change that kind of thing. And then there's some inventive model building and problem solving, and eventually get to the class that I'm currently working in, the programming class, which is where they're building robots and programming them using computers. Some of the robots are invented, some of the robots are pre-canned. It's a good mixture, and I'll go through that class. The Lego Logo class is programming class, which started with Logo, the language. 6 to 10 students, ages 10 to 12. They're all very highly motivated, and in fact, if they don't behave, they're just booted from the class, and they know that. They respect the teacher that runs the class enough that, oh man, one warning, they toe the line. One of the things that this program focuses on is one-on-one or maybe one-on-two teaching. This is insane. No school could ever withstand, support this kind of education unless you have a lot of both parent and older student teachers, essentially. So it's extremely intensive and focused with a high, 1-to-1 or maybe 1-to-2 teacher-to-student ratio. It's in 2 terms. The first term is building some simple models and learning some simple programming techniques. And then the second term, the whole class works together to build a big display that they put on for the public, either at the local zoo or at local schools and that kind of thing. So we put together a program, and then the children take the program out to the community and present it. So they have a bunch of social skills in doing presentation along with the engineering skills. Again, this taking these little proto-geeks and turning them into proto-geeks with a modicum of social skills. The original computing environment was broken into three parts. We had the little RCX, yellow RCX bricks that were programmed with a system called RoboLab. There's 2 commercial RCX programming systems. The one that came with the RCX, that's the usual commercial one, and then there's the one from Pittsco, this educational system called RoboLab. They're both blocks-based languages where you drag these icons around the screen and hook them up with these wires. God, I can't imagine. I taught that for 2 months, and I said, really? Really, you have to have hand-eye coordination to program? This is not good. And of course, I couldn't figure it out. The other one that they do is they use the Macintosh running OS 9. OS 10 is not good enough for this class. They're going classic. In fact, I think one of the machines is still running Mac OS 8. Maybe even 7, I don't know. In any case, they use a low-go programming language. There's a little control box that connects to some 6-volt motors. It's a pretty fun environment. The other thing that they used, which was the first system they started off, it was an Apple II, not a Macintosh, Apple II GS. How many of you used an Apple II GS in your childhood? Yeah. Yeah, I know, some of you. Now, as you know, the Apple II GS has a 16-bit processor. Yeah, correct. Yeah. Ooh. It's a 16-bit processor. It's emulating the old 6502 because, 6502 was the pinnacle of processor technology. So everything has to emulate the 6502. Used floppy disks. The kids show up at the class one day and you say, please put this in the computer. They look at you like you're from Mars. What the heck is this? Now they are, of course, the modern new floppy disks, the 5 1/4 inch, the small, compact ones. Of course, when I was a child, we used the real floppy disks for our microcomputers, but our real computers used punch cards or paper tape. In any case, so all the software is on floppy disks. We use a couple of Lego kits from this era, the Lego 1090 Technic Control Kit. I got pictures, I'll show them to you. Oddly, these machines are getting older, along with the rest of us. These machines were purchased by the teacher literally 25 years ago. Yeah, one of them died last year, or 2 years ago, and it was a real wake-up call. It's like, how many of these do you have? I have 3 more. If one of these die every year, what are we doing after that? Yeah, here's what this machine looks like. Now this picture has a window system on it with little icons. That's fiction. I have never seen anything that fancy on these computers. It's text mode. It's awesome. The Legos, of course, we're using the, I don't know, how many of you have ever seen a Lego? Yeah, all of you. Yeah. They used the Technics, which were introduced in the late 70s, way more stable than regular Lego bricks, so you can actually build things that move and don't fall apart. These all use 4.5 volt motors. 4.5 volt is an important number here. Remember that number. They came with touch sensors and light sensors. They came with little lights. Here's the Legos. This is the kit that we're using. Yeah, isn't that awesome? Yeah. So this is the kit that they were using for the Apple II. Here's the motors and lights they were using. This is the 4.5 volt motor. These are actually totally ungeared. Those are just a motor in a piece of plastic. So guess how many RPM that motor runs at? Sufficient. Yeah. You can get it to go. You can get it to go anywhere between way too fast and oh my god, it will never work. And then we have incandescent bulbs in Lego bricks. I don't use those anymore. But the Lego motors are actually really nice. They're sturdy and solid. They don't have any gears to break inside. They've survived for 25 years, and I'm pretty sure they'll outlive me. The sensors, we have 2 kinds of sensors. We have these cute little light sensors here on the left. They have an IR. I think they're visible. I haven't looked at them recently. I haven't used them in a while. A little visible LED, and they have a little photo transistor in them. And then we have these little push buttons. To go with the light sensors, they have these cute little discs that have light and dark bands, so you can actually count rotations. Now the problem with the light sensor, all of this stuff is hooked up with 2 wires. Anybody see a problem with having an LED and a sensor hooked up to your computer with 2 wires? Yes. There might be a fun, where does the power go? So what this thing does is it modulates a signal. It sends a pulse down the wire, turns off the power, then listens. Sends a pulse down the wire, listens. So what it's doing is it's sending power occasionally. There's a little capacitor in there that keeps it charged, runs the electronics, and sends a signal back. No. Do not like. It's cool. These things actually are totally symmetrical. You can flip the wire around and they still work. It must have like a full wave rectifier in there or something. I don't know. I never tried to figure out, I tried to figure out how those worked for about 10 minutes, and it's like, no. So in this Apple II GS class, what we used to do is we used to do three different things. We used to spend a day or two discovering Logo, just playing with it at the command line, turning the lights on, making the motors go, seeing what the sensors did, which was really cool. I liked the fact that you could do that interactively. It was a really quick introduction. You could learn the language in about 2 seconds. Logo. How many of you have programmed in Logo? Awesome. Yeah, it doesn't take long to learn the syntax, right? Yeah, it's words and spaces. It's pretty awesome. And then we actually built a pre-canned model, the washing machine. The washing machine was because what you would program in the washing machine is a sequence of operations. You'd close the door, and it would wash the clothes, and it would spin the clothes, and it would dry the clothes. So it very much matched what we'd be doing in the second semester, which is building this complicated interactive model that did all kinds of crazy stuff. So the washing machine was cool from that perspective, but really, a washing machine? 10-year-old kids not excited by washing machines. The other thing I added to the class was a bumper car, which was a lot more fun because it was interactive. It ran around on the floor. It ran into people's legs and broke all the time. Perfect. And the kids, of course, could chase it around, which for 10-year-old children is awesome. They love to move around. Some of the students blazed through this class and were done with the bumper car by the second day, the second class period. Some of the students took 5 weeks to get this far. Was there a correlation between talent and speed? No, absolutely not. Some of the students were just were interested in kind of touching the topics and getting on past. So we would end up spending a bunch of time playing with the bumper car, using different sensors and doing a bunch of stuff. The class couldn't quite scale enough. It was pretty good, but it couldn't quite scale enough. Here's a picture of the washing machine. Yeah, it has a little wheel there. There's a little black tire in there that's supposed to be the actual wash, and it's got motors and sensors and lights. Yeah, it was fun. So what was my basic plan? Well, the 25-year-old hardware was dying. Programming Logo is not all that useful for the kids because it's Logo. Not a lot of, and most of these children were interested in going on. Well, in fact, I'll tell you a little more about that later. A lot of these students are going on to middle school and upper school, and they're wanting to do science projects involving computers. 4 of them out of this program have now gone on to do Arduino-based science projects. One of them did an automatic pointing solar cell. One of them has done an automatic metal detector. We have a linear motor car. We have a robot that follows you around. All kinds of cool stuff with Arduino. I wanted to bring Arduino down a couple years, give them some introduction, and let them know that they could do science fair projects that were cool and fun, giving them a computing and engineering possibility instead of just the usual bio crap that they were doing for science fair projects. So my plan was to bring Arduino into this class where I could have a little more structure, take the Apple II away, swap in Arduino and Linux, and then eventually profit. Yeah, sure. It's all Legos, right? How different could these two environments be? Could we use the same models? Do I want to program the washing machine? No, I decided that was dumb. What are the differences between using that old Lego environment and moving into an Arduino-based environment? Well, the Apple II GS was really hard for these kids to operate. These kids have had their own computers in their hands at the school for 5 years. They're used to WIMP interfaces. They're used to clicking and touching and doing stuff like that. Trying to get them to figure out how to operate the command line was actually hard. It's like, well, what do you mean I type Apple F to go to this part of the window? Where's the mouse? Yeah, not so much with the mouse. However, the Logo environment was all interactive. If you wanted to turn the light on, you could just say, talk to output 1 on. And that's all you had to do and the light would come on. It was awesome. They could get some immediate gratification. Getting that immediate gratification in the Arduino environment proved to be one of my learning challenges, getting them to the fact where they were getting immediate gratification as early as possible in the class. When we moved to this when we moved to the compiled environment, there is no immediate mode. You always need to have a complete program, right? You can't just have a little program fragment. There's no way you can say, oh, I'm going to write this little function and call it from the what? Yeah. The other big problem is that showing values, like what's the current value of the light sensor? Well, you can't just ask, type in, listen to blah, and then get the input value that way. You actually have to write a program that prints the value, and you have to monitor that value. So it's this huge overhead that we used to be able to satisfy very quickly in an interactive environment. The other big change is that Logo is a heck of a lot easier to show kids how to type in than C. None of the students ever completed a program without missing at least one semicolon. It is surprising how quickly they grasped the notion of different kinds of bracing and how they grasped the notion of expressions. That seemed all pretty okay to them, but it was the semicolons that kind of got them. And of course, C has types. So you would say, you declare a variable int foo. Well, int? What does int mean? That took a lot of discussion. We kind of glossed over a lot of that stuff. The other thing is the Logo stuff came in all this nice shiny plastic, right? It has this nice shiny plastic cases. They had shiny little connectors. It was all nice and plugged together. What does Arduino give me? It gives me a row of pins. Awesome. What do I do with that? But in any case, I decided to go with the same class structure and try to figure out how to adapt it. So I wanted to explore the Arduino environment, build some pre-designed models, and then extend to some more custom models if they had time. Exploring the Arduino was to present the hardware. I wanted to show them what the hardware was like. I had enough. Fortunately, one of the awesome parts about Arduino is they're so cheap, I just had a lot of them. So it's like I would throw a bunch of Arduino stuff on the board and say, well, what does that one look like? And so the kids got some immediate, as soon as they got into the class, there was a bunch of circuit boards on the table. It was amazing how many of them had never seen circuit boards. It was even more amazing how many had never seen through-hole or surface mount components. It was weird. It's like, I look at my office at home and I'm knee-deep in circuit boards. But these kids had never seen them unless they'd been, breaking something. So seeing a circuit board is usually bad. So I just threw a bunch of circuit boards on the table. Then I would show them some very introductory program, doing some very simple stuff, and we'll show that in a while. I had to, because it was C, I had to start with a complete but trivial example. So I gave them a complete program that did nothing. And I said, if you type this in, it will be happy. And they're like, yeah, happy, so what? If I type nothing in, it's happy too. And then we expanded it a bit at a time. The other thing that I learned very slowly was that my job was not to tell them what to do. My job was to ask them questions and let them figure out what to do. That took me about a year and a half. I'm kind of a slow learner. The next set of slides are actually from the class, and I'm going to just blaze through these. There's not a lot to show. Obviously I showed them the Arduino CPU. We're using a little motor controller with a little H-bridge chip, nothing fancy there. I actually have about 4 different kinds of H-bridge boards, and they're totally, God, they're all awful. They put the H-bridge all over the top of the other outputs and the other inputs. It's a mess. Oh well. The other thing that I chose was I found these little wiring shields, and there's a couple different styles. These are fabulous. These offer you little plug-in clippy bits, so you can clip cables in. And where you don't have clippy bits, they just have 3 little pins. So I could get these fairly standard cables. They just had 3 holes, and I could connect all my motors and everything else using I could build standard cables. Because one of the important things is that, guess who gets to wire this stuff? It's not me. The students, of course, wire it all up, so I wanted it to be easy. This provides power, ground, and signal for all of the inputs and all of the outputs. It was weird. I ordered a bunch more of these in the fall, and along with some more motor controller boards, and the price on these was $0. And it's like, you're giving those away? Okay, I'll have 10. And yeah, they really showed up, and they actually were free. I did not understand that, but whatever. What? So this was cool. I showed them this. The other things I did is I built a new light sensor because the light sensor from Lego was bizarre and bong hits. And what I did is I just put a little IR LED and an IR phototransistor on some wires and wired them up with resistors. So when you get light, the signal goes high. When it gets dark, the signal goes low. Pretty simple. But I used IR. Why did I use IR? Well, I thought it was cool that you wouldn't be able to see the light. I was wrong. But then because one of the things the kids have a really hard time understanding is that if you don't turn the LED on, it doesn't work, because you don't have a lot of IR light in your environment currently. So you have to turn the light on and shine it on something and get a reflection. If I did this again, I would work harder to find ambient or visible light sensors, because it gives the kids a lot more visceral response. However, trying to get large phototransistors that respond to visible light, yeah, I can't find any at this point. They're all IR only, and they actually clip off below the red range. It's kind of annoying. I found some, my little tiny micropeak boards, micropeak, oh, this one. Where did it go? That one. This one has a visible light phototransistor. It's right here. That's a micro USB connector. That phototransistor is a little smaller than that. I have put one of those on wires. It's, the phototransistor is about this big. So there are visible light phototransistors that all just surface mount only. So I showed them that, and then we start talking about how the Arduino hardware works. You all know how that works. So we talked about, the different kinds of outputs, analog inputs and analog outputs. We talked about digital inputs and analog inputs. I showed them the Arduino program, which is, the setup function and the loop function. I talked about declarations. You have to, of course, in Arduino, you don't have to use any declarations if you want to do simple programming. You can just put the pin numbers everywhere. Trying to teach the children the difference between have to and it's helpful for you to, when you're reading the program, is really hard, because most of them just want to type in the program and see it work. So trying to get them to actually use useful variable names, it's like pulling teeth. But I let them use whatever names they want, and sometimes it's like, Jane's Light, or Billy's program, or Billy's motor, or whatever. It's kind of funny. It's fun to watch them think about owning the program more than having the program describe what they want to do. So the file names were invariably their own names with some exclamation marks or whatever they wanted, never descriptive. It's like, okay, whatever. We talked about setting stuff up and using the serial debugger. Then we talked about what you do in the loop and what you do in the and how you do some simple debugging. We talked about this. I just put in an appendix. I didn't even show them any C syntax to start with at all, because they were going to have to refer to the appendix every time they did stuff anyhow. And so I didn't want to I was trying to get from they show up at the class to they have a working robot as quickly as possible. So we typed in our first program. I talked a lot about what happens when you do something wrong, what's the computer going to do, so you can help figure out what's going on. Then, how do we get the debugging stuff working? Because they're going to need to print out values, especially when you start using light sensors. And, work with that in a fairly concrete way. And then we wrote a little program to turn on a light. The Arduino boards that we're using, the Dueme Lenovas, have a little tiny light on pin 13, and you can just turn it on. So we didn't have to plug anything together. All you had to do is take the USB cable from your computer, plug it into the Arduino, you can turn a light on. Woohoo, a light. Yeah. And then I asked a bunch of questions about, well, what happens if you do it wrong? What kind of diagnostics is the system providing for you? Well, in the usual traditional AVR way, when you do something wrong, it just doesn't work. That's your diagnostic. It's, like the kernel. When the kernel does something wrong, you get EPERM or E-access. It doesn't actually give you a useful error message. It's useful for children to get inoculated at this point if they're going to go on and use Linux in the future. Yeah, to expect the system to give you no hints about what went wrong. And you have to build your own printf debugging. So I did teach them printf debugging, just like the kernel. I felt I was doing my job. We talked about how to blink the light, and this introduced the little notion of delays, and all of a sudden we're getting a little sequencing in here. All of a sudden you can notice that the loop program gets executed multiple times. What happens if you turn the on and off around so they do things in opposite orders, and the kids are like, oh, then it'll, and they try it, and it's like, oh, it does the same thing. It's really neat for them to think through why that might be true. It's kind of fun to watch younger brains in action. They learn faster than I do, but they just don't know as much. And we talked about using buttons because we wanted the robot to interact with the environment. So we talked about, so the buttons we have, of course, are just switches. They're not switches with a resistor, they're just switches. So in order to get the button to work at all, I had to go through usually about 15 minutes of talking about a pull-up resistor. And that was a mystifying notion. Why would you need a pull-up resistor in this environment? Well, it's kind of cool. It's like some of them, you could see it's like, well, of course you need a pull-up resistor, because otherwise it's, you know. So we talked about, I don't know, introducing this concept was like, well, it's going to give you a I don't know value, and what's the computer going to do with an I don't know value? And the student's going to go like, well, I don't know. So it was kind of cute. And of course, we tried it without the pull-up values, and when they saw what happened, it's like sometimes it worked and sometimes it didn't work, which was kind of cool. Arduinos are at least random in that way. And of course, a lot more questions. And we talked about light sensors, and the key with the light sensor is this serial debugging line right there. You want to find out what the value is, because the value depends very much upon what material you're shining off of. And in particular, we had a bunch of masking tape that we're using in one particular project, and one of the colors was bright white in visible light and black in infrared. It was really weird. And in fact, one of the infrared sensors that I had saw one tape as brighter than another, like the values were swapped between the two sensors. It's like, really? Okay. So the kids got to learn about, you know, the difference between theory and practice. Yeah, in theory, there's no difference. Then we used the motors, because the motors are always fun. The motors break things. The motors fall off the table. The motors were great fun. We talked about how to make the motors go backwards and forwards and change their speed. And then we built a bumper car, and this was kind of fun. This is the advanced elastomere technology for attaching the Arduino to the Legos. Those really are just rubber bands. I haven't figured out how I want to do this, but my God, this is a simple way, and it works surprisingly well as long as the model doesn't actually fall off the table. Fortunately, Arduino boards are cheap. As I say, I buy them new every year practically at this point, just kind of as a matter of, oh my God, all the other ones are broken now. So this is a simple model. Of course, the current model was not designed by me. I designed a model that was terrible. One of the students last year designed a new model, and of course, I used his model, and we now call it by the student's name. So that the other students understand that this is not a class that was constructed by me, but a class that grows over time and learns from the participants, and that if they do something really cool, we'll remember them. And that when they come back 6 years later as teaching assistants, they can hear us talking about things that they did as younger students. And it gives this continuity and also the knowledge that the parents and teachers are watching. The way that we generated instructions for this model was to actually complete the model and then take it apart, taking pictures, and then play the pictures in reverse order. A fabulous way to generate construction. Because you know, construction instructions, because you know it actually works. That was pretty fun. Yeah, you notice the fabulous attachment technology. Yeah, it was great. Then, of course, the way that I taught the children to program these models was by only asking questions. I gave them enough. I had a huge, a bunch of additional material in an appendix about how specific parts of the system worked. But I didn't show them any complete programs at this point. You know, how do you want to hook up the wires? How do you want to check to see if the buttons are getting pushed? How do you tell, you know, which way does a robot need to go when this button gets pressed, and that kind of stuff. And eventually, usually within about an hour and a half or so, they'd have the robot zipping back and forth around the ground, bumping into their legs, and they'd kick it, and the pieces would fall off, and they'd put it back together. They just had a great old time. And of course, one of the things, so if for students that had gotten to this point faster than other students, we had them try out a new sensor. It's like, here, I have an IR distance sensor. This is one of these little sharp distance sensors that a lot of Arduino projects use. These are a disaster from a noise perspective. Ever looked at the power supply leads coming out of these things when you plug them in? Oh my God, it's noisy as hell. That's a different experiment. In any case, we experimented with these things and patched the program and tried to figure out how to get them to work. These are fun to use. And so that gave students kind of an additional thing to play with. The next thing we did is we built a little line following bug. Now the cool thing about the line following bug is the line following bug doesn't have any notion. It doesn't have any static stability. What the line bug is supposed to do is it's supposed to follow the edge of the tape, the point where it is neither light nor dark, but both. So what does the line bug have to do? Well, it works just like a CD reader, right? It's going to see if it's too light and turn to the right, and too dark, it turns to the left, or vice versa, whichever the students chose. Getting them to think about this notion of dynamic stability really for some of them was like, wow, it's not just a static notion. It's this notion that this thing is constantly in motion and following the edge of this thing. It was really interesting to watch how they thought about this process, not of following the line as some static decision, but as following the line as a dynamic process of moving to the left until it got light and moving to the right until it got dark. And that was a lot of fun for them to learn because it taught a lot more interesting programming concepts. And of course, you got to use 2 motors. And the cool part about the line bug is you see the, all the tape all over the thing. What we have is a big black table, and we just take masking tape and stick it down all over the table, and the robot follows it all over the table. So the kids usually spend about 15 or 20 minutes after we're done building line bug sticking tape all over it and trying to see what it will do. And for the students who were interested, we could actually extend that into a huge number of different algorithms for tuning this process. We had one student who was trying to turn, occasionally turning motors backwards and forwards and trying to follow the line and looking at the precise value of the light sensor to try to follow it more closely. It was amazing. So that was fun to watch. I learned a lot. I probably learned more than the students did doing this particular class. One of the things that I learned was that when you're teaching programming to small children, even older children, some of these kids are in middle school. These kids have been typing since they were like 2 years old. I don't know, most of them, right?
What's middle school?
Grades 6 through 8. Ages 12 through 14. Yeah. So even the kids of that age, they type surprisingly slowly. Some of them could like type at maybe 10 words a minute. Most of them couldn't manage that. Most of them were still hunting and pecking. So I would, what?
It's not texting.
They're not using, some of them were using their thumbs. It's amazing.
You're kidding.
No. Oh no, they type with their thumbs.
Shoot me now.
Oh yeah. So one of the things that it took me about a year to learn was you don't have them write a new program from scratch every time. You take an existing program and you change it in small ways because there's way more educational value in typing small amounts of stuff to an existing program than starting from scratch all over again. So a lot of the educational stuff I was trying to do would take an existing program and modify it in small ways. And I'm trying to get better at that. But the less typing they have to do, the more fun they're having. And I think probably the more concepts are getting in front of them. The other thing, of course, is that even in the Arduino, or especially in the Arduino environment, the output from the compiler, the error messages and warnings are utterly incomprehensible. On the Arduino IDE, it has this tiny little window for compiler messages, and if you have more than one, they go in this lovely orange on black text at the bottom of the screen. And you're trying to figure out what this says, and it's got line numbers in it. There are no line numbers in your code. They have no idea. So I could have spent a long time trying to figure out how to teach the program to read the kids to read the error messages. No, I gave up on that. I read the error messages and say, you've got a mistake here. So it's basically parsing the error message for them. It would be nice if the Arduino environment would like highlight where the errors were. That would be great, but no, it doesn't. So that's something that would be nice to see improved. In any case, wow, that took a long time. After I pushed the button, it sat there for like 3 seconds. So one of the important lessons that I've learned in this process was that when you're teaching kids, you don't tell them anything, you just ask questions. You may tell them a little bit of didactic stuff to get them started, but the more time you spend asking them questions, the more engaged they remain, and I think if they're engaged, they're probably thinking a little bit more about it and probably learning more. The other thing is it makes the child feel like an expert. If the teacher is constantly asking the child questions in a positive way, not, why didn't you do your homework? That doesn't ever help. But getting the child to think and leading them through the answers, the children feel more in charge and take ownership of the class, and that's helpful. The other thing, of course, was using the children's models instead of my own models for future kids, and every year we change the models a little bit. We adapt new ideas from the students that were in it last year. It makes the kids feel like they own the class, and it makes the kids feel like it's their class with us as assistants and not our class with them as passive watchers. The other thing is that, of course, this seems obvious now in retrospect, children have different learning styles. Some are active and noisy, and some are quiet and like to listen and like to watch. So one of the things that I learned was to respond to the kids individually, and for children that were a little more reticent to talk, just leave plenty of silence. Put some space into the class, let the kids engage at their own speed. When the kids had a model completed, we'd have the other students who are doing programming in the other systems come over and watch showtime, and the kids would ask questions, and they could they could show off what they had done. They would explain to some of the other people other kids who'd been in the class new things they had tried, and of course steal their ideas for future classes, because they are thinking a lot more about the mechanics and a lot less about the teaching process than I am, and so they actually have a lot more time to think about how to improve the models and the programs. The other thing is, I was kind of surprised that I could learn to teach children. I never thought I would have that skill, and I certainly never thought I would enjoy it. So thanks. Hope you enjoyed the talk today. If I have other questions, I think we have about 5 minutes.
5 minutes,
Yep.
Any questions?
Yeah, up here.
I was wondering if you'd looked at sharing the materials you produced, or making them so that other teachers could use them.
Right now what I have is I have an ugly PowerPoint slide deck that I've been editing over the last couple of years, trying to get some concepts down. I can certainly share the current contents of that slide deck. It's not very well organized or ordered. What I've decided that I actually need to do, because the slides are now getting so dense with text, I think I can actually turn it into a text document and actually have lessons in text form. So that I would love to spend some time doing that. I think I'll publish the slide deck as is and hope to refine it in the future and turn it into a text document instead of saying, no, please wait. So I'll put those slides up on my wiki page in my house.
Keith.
Yep.
It seems like a big jump from the Legos to Arduino and from Logo to C. Do you think it would be good to have some kind, I know there's not really anything there, but have some kind of middle ground between them to ease the kids in from that kind of simplistic start to using Arduino and C?
The concepts, fortunately C is a very low-level language, so there's not a lot of conceptual difference between what Logo is doing and what C is doing. Really the barrier is syntax. And so if you help them through the syntax problems, they actually pick it up surprisingly quickly. The concepts in Logo and the concepts of C are very similar. You're talking to a device and telling it to do something. You're listening to a device and asking it what its current state is. It really is a matter of making sure that the concepts are explained concretely enough and with reasonable examples that they understand that the syntax is just a way to communicate with the computer and not really the conceptual underpinnings. There really isn't any difference between Arduino and Logo at that level. So the syntax is a problem. Getting them through the syntax, it usually takes about 1 class period. Yep.
Sorry, one more here.
Yep.
Hi Keith, I run a very similar program to yours in the vacation, and one of the things I found really good is the show and tell to the parents at the end of the class. How have you found that in your experience?
What we do during the class is a show and tell with the students who are there, and at the end of the class, as the parents come to collect the students will show off the models to the parents. A lot less formally. We don't have all the parents watch. The parents of each student come in. What I've noticed is that parents of the other students are very uninterested in the other children's activities, although those children would be interested. And so we have the parents of the children themselves come in and watch what's been going on. It seems odd to me that the parents are so, I guess it's normal for parents, but they come in and very focused on what their child has done. And because we have that one-on-one student-to-teacher ratio, then the teacher and the parent and the student can all, enjoy the student's progress together. That works nicely, yeah.
You said going from Logo to a C in Arduino, there's a loss of immediate sort of, it does stuff. Have you thought of running a simple sketch that takes input from the computer and then turns lights on and off when you hit a key on the computer? or is that going to produce an intermediate step between this is the hardware and this is C and there's this magic stuff in the middle?
Yeah, I would have to think about that. And that might be an interesting way to demonstrate what the hardware could do. But I don't think that's a lot different from the busy boxes they played with as toddlers. It would have buttons that would turn lights on. It doesn't give them any notion of why. It only gives them a notion of how. But maybe, yeah.
Sorry, to follow on, I know that it's really cool to see the robot running on its own, but that means you have to program in C on the Arduino. If you keep it tethered to the computer and program it in Python or something, is that, somebody else mentioned, an intermediate step that's a little more forgiving than C?
I think Python is just punitive. What I want, as I say, my goal is to get these students to the point where they can use this robotics environment to do science projects in their older school years, and getting to the point where they're using a real computing language in a real computer. I don't see any reason to do some intermediate Python disaster.
On that rather contentious statement, we'll thank you for your talk, and I'd like to present you with this gift.
Thank you, buddy.
Thank you.